Okay, our agenda today is to go over some problems for homework that maybe people either email me this weekend, or I noticed that there was people having problems on certain homework problems. So we'll do that out of chapters 1 and chapters 2. So we'll start off with a chapter 1 problem. This was assigned 85. Let's see, was 85 assigned? I think it was. It's a rotating cylinder inside of a fixed cylinder. Picture on the board shows that. I'll read it first. The space between two 6-inch long concentric cylinders is filled with glycerin. Viscosity is given. The inner cylinder has a radius of 3 inches, and the gap between the cylinders is 1/10 inch. 1/10 inch gap shown there. Determine the torque and power required to rotate the inner cylinder at 180 revolutions per minute, RPM. The outer cylinder is fixed. Assume the velocity distribution in the gap is linear. Okay, I didn't put the 6-inch on there, so let me put that on the picture too. 6-inch from here to here. All right, so there's the picture. If you look at a view from the top, okay, there's the outer cylinder. Here's the inner cylinder. Inner cylinder is rotating. That's the radius R inside. This is the radius R outside. The outer cylinder is fixed. The inner cylinder is rotating at omega. The glycerin is between the two cylinders, and this is gamma and mu. Okay, so we can start off. Now we know, let's take the assumptions he said. He said assume the velocity distribution is linear between the cylinder and the fixed outer cylinder, the gap, in the gap. So it's going this way, so that means that this would be the velocity here, and then at the outside, the fixed side, the velocity is 0. So it looks like this. He said it's linear, so it's shown there as linear. Now, first of all, a torque. The torque is a force times a momentum, or force times distance. So torque is equal to force times distance. There's a force on the inner cylinder that's rotating. That force, I'm going to show it here. There's the force. The distance, of course, is the radius R inside. There's the force. So we can go ahead and say that the torque, force times distance, and that's equal to F from right there, times the distance, which is R inside. Now force. That glycerin is experiencing a shear stress. And at shear stress, we'll put it up here. Shear stress is tau equal mu du dr. The velocity u is a function of the radius r in the picture. U is the velocity anywhere in that distribution. Capital V is the velocity at the inner cylinder. Du dr on the surface of the inner cylinder. But he said it's linear distribution. So if you recall, we can replace this with mu delta U over delta R. And if we do that, we get mu delta U is the velocity here, v minus 0 down here, v minus 0. And then we have R outside minus R inside. So, shear stress tau equal force over area. So the force F equal tau times A. Tau times A. The air, put in tau first. The area is the area that the glycerin touches the inner cylinder. The area the glycerin touches the inner cylinder. Circumference 2 pi r times the height L. 2 pi r L. R inside L. Times the Ri, the distance for the torque calculation. So that's equal to mu v, let's put 2 pi out in front here. 2 pi mu v L over R outside minus R inside times R inside cubed. That's the torque T. I'm not going to put the numbers in, you can do that straightforward. Okay. Now, that answers the first part. Find the torque. Now the power. Okay, find the power. Equal torque times the speed. Torque is T, speed is omega. So take that answer, put it up there. Omega, be careful. This has to be in radians per second. Okay, so we have to convert. What was it given to us in? RPM, 180 revolutions per minute into radians per second. Why? Because the angle has to be dimensionless. You can't put revolutions in there. You got to put the angular rotation in radians, dimensionless. So if you do that, the torque down here is going to be force times distance. That would be pound-feet. Multiplied by omega in radians per second. And don't forget, radians is dimensionless. That's power. That's power. Work per time. What's work? Pound-feet. Work is pound-feet. Divided by time, what do you get? Power. Yeah.
For the torque, shouldn't it be Ri squared because you have Ri?
Oh, let's see here. Yeah, hold on. No, it's Ri. Thanks for mentioning that. I was doing the power. Yeah, thank you. I was doing the power. When you multiply it by that guy over there, yeah. Let's just make sure. Tau up there is equal to mu du dr. Got it. V minus 0. V r minus r 0 mu. Area is square feet, got it. Circumference, pi times d, 2 pi r, times what? L, Ri. Yep.
Okay.
Thanks. Okay, to convert this guy, you know, what's one revolution? 2 pi radians. 2 pi radians per revolution. 60 seconds in a minute. 2 conversion factors, here to here. Okay, so that was one that was in the chapter 1 on the use of the shear stress and viscosity mu. You had 3 assigned in chapter 1 with shear stress, so this was the 3rd one in that set. Okay. Probably we're all here now, so I can talk about the exam for a few minutes in case I get working to the last minute today. All right. It's going to cover chapters 1 and 2, as I mentioned. It's going to be closed book. I'm going to give you about a 4-page handout of additional information. In that handout, I think it's 5 pages. In that handout is going to be, in the appendix, the properties of various fluids, tables B1, B2, B3, B4, and in the inside front cover, which we use, table 1.5, 1.6, 1.7, 1.8. So inside front cover, appendix B, properties of water and air in both BG and SI as a function of temperature. Okay. You'll be given that. You'll be given under fluid statics the table. It's figure 218. I'm going to give you figure 218. Locations of centroids, moments of inertia, areas of typical geometric shapes. Figure 218. I'm going to give you, at the end of each chapter, it's called a chapter summary, a study guide. In that section, there's a big red box that has quite a few of the important equations in that chapter. I go to chapter 2, and I go to the same thing at the end of every chapter. There is a red box, and what the author thinks are the important equations in that chapter. Now, they're not the only ones, but that's what the author wants to emphasize. So I'll give you those, chapter 1 and chapter 2. All the properties, okay, I told you, fluids. I'll give you the properties for moments of inertia and centroids of different geometric shapes from the figure 218. You'll have that, for this exam, that package has everything through the whole course in it right now. So I'll pick them up when you're done. I pick them up, and I'll give them back to you then for the second exam, and give them back to you again for the final exam, the same package. Okay, now besides these equations in these red boxes, you're allowed to bring with you one sheet of paper, 8.5 by 11, both the front and back sides, with anything else you think you'd like to have for the exam. It might be equations that aren't in those red boxed equations at the end of the chapter. It might be a homework problem you especially had difficulty with. It could be whatever you want on there, whatever you want. One sheet, both sides, 8.5 by 11. I don't care if you photocopy every homework problem you've got, postage stamp size and put on it. I don't care. Drive yourself crazy. It's just a crutch. Sometimes people don't need it, but it's a nice crutch. You feel more comfortable with a little equation sheet by your side. That's what it's for, okay? Yeah.
So we're going to be given the equations in the back of the book, or the equations at the end of the chapter, as well as the tables in the back of the book. And then we have paid for additional things.
That's right. Things that you had difficulty with, and maybe some hints about stuff. If I get a problem like this, make sure I do this. Your own little stuff that would make you feel better. Okay, let's see, what else? Oh, probably somewhere 25, 30% chapter 1, 70, 75% chapter 2. Chapter 2 is much longer, and it's much more beefy. So of course the emphasis is on chapter 2, but there will be problems from chapter 1. Probably 4 or 5 problems, depending on how long they are. I gave you online Blackboard at last year's exam. That's 50 minutes, 3 problems. So we have an hour and 15. So 4 or 5 problems. Weighted by different amounts. Some might be 30%, some might be 25, some might be 20, so on and so forth. Okay, let's see, anything else on that? I don't think, anything else that I missed? No? Okay, an hour and 15. Oh, office hours. Let's see, okay. Tomorrow, you know the regular office hours, 9 to 11. But on Wednesday, normally 12 to 1, so I'll go from 11 to 1. 11 to 1 on Wednesday before the exam. Last minute questions. It's best by that time just to sit back and relax. Don't try to cram, as you know. You've been through too many tests to know how to pass tests. Don't cram for the last minute. Okay, anything else on that? Okay, so this was our only chapter 1 review problem, okay? Now we're going to go on to chapter 2. Okay, I guess I'll put it right here, this spot for it. 115. Two hemispherical shells are bolted together as shown. You've seen this picture. The resulting spherical container weighs 300 pounds, is filled with mercury, supported by a cable as shown. Container is vented on top. 8 bolts are symmetrically located on the circumference. What's the vertical force each bolt must carry? We have the bolts along here. It's hung up to the ceiling support here. It's filled with mercury. Three foot in diameter. Okay, let's see. The container itself weighs 300 pounds. Top and bottom. Okay, find the vertical force that each bolt must carry. Okay. Two ways to do it. Let's see which way we'll do first. Let's do it this way first. Here's the bottom half of this thing. We're gonna look at this picture, bottom half. So it has mercury in here. The shell is here. Okay. There's pressure on the top here. We'll call that just, let's call it P. Okay. And now we're going to draw a three-body diagram of this. So take it again. And This is my free body diagram. And we'll call the force due to, now show the forces on this. Bottom shell. Plus the mercury. Okay, first of all, there's a force here, downward, due to the pressure on the top, call that F sub P. There is a weight of the shell and a weight of the mercury. And then, of course, there's the bolt force. It depends how you want to do it. I'm going to show it like this, a big fat arrow. Force bolts. So, there's a free body diagram. Then somebody says, you know what, I don't like that free body diagram. I'm going to do it my own way. So the second way, draw a free body diagram of the here's the shell. Okay, just a shell. Okay, so I'm going to draw a free body diagram of this now. So take the shell. Okay, number one is I have the bolt force acting upward, holding this thing together. And let's see how I label this thing. There's the weight of the shell. Okay, I call F sub B the vertical force. The weight of the shell is acting down. And then I have the force acting down on a curved surface. F sub B is the vertical force on the curved surface. We did that in chapter 2. Two different free bodies. One includes the mercury, one doesn't. Of course, the bolt force acts to the center of the hemispherical shell. So I put it in the middle there. I don't show it here, I don't show it there. You could, but why do it that way? Okay, we'll do each one. The top one up here, let's take this guy. Summation of forces, you know, he likes to call Z upward, so we'll call it Z upward then. Okay. So, and I'm going to call this just FB for bolt force. FB, this guy right here, is equal to these three guys going down. F due to P plus F due to the, plus the weight of the shell plus the weight of the mercury. Okay, let's do each one of these then separate. FP, there's the pressure force. What's the force equal to? Pressure times area. What's the area of what? The shell or the mercury? No, the mercury. Mercury has a pressure on it. Okay, so the pressure times the area of what? The mercury. What is that? A circle. Pi r squared. So P times our pi r squared. The weight of the shell is the weight of the shell. Now, the weight of the mercury. They're given gamma of the mercury, I think, in the problem. Yeah, we know what mercury is. So gamma Hg. Okay, so we have our weight of the mercury, gamma Hg. Sphere, pi d cubed divided by 6, half of that. 6 times 2 is 12. Volume of sphere is 1/6 pi d cubed, pi over 6. Okay, so there's that guy. The pressure right here, the pressure where my fingertip is. The pressure where my fingertip is. Here's the key word he says. The container is vented on top. Oh, thank you very much. The container is vented on top. There's a hole right there. Mercury's not squirting out. Mercury's sitting in that thing. So guess what that pressure's going to be right there? Well, I'll tell you that, sure. How far down are you from that hole? R. That's how far down you are. What's the pressure down there? Chapter 1, chapter 2. Gamma times the distance, gamma times R. So that pressure, gamma times R. This guy right here is 2R. 2 times 2 is 4, times 2 is 8, 8/12. So we have 2/3, 8/12. Cube, 2R, 8/12, R cubed. That should be, okay, got it. And gamma again, so gamma in there. We won't worry about subscript gamma Hg because it's just one gamma mercury. Plus weight of the shell. Okay. There's the answer. I'll do it this way now. All right, by the way, the answer is 1/8 of that, because he said, what is the force in 1 volt? This is the force in all the volts. There's 8 of them, so 1/8 of that thing. All right, same thing, some forces in the z direction. Okay, what's going up? F volts. Okay, FV. What's going down? The weight of the shell plus FV. Okay, FV. I'm doing it now by the way that I did for a curved surface. So here's the free surface of the mercury. Here's the curved surface of the mercury. Okay, what's the vertical force? Okay, on that curved surface. It's gamma times the volume of the fluid above the curved surface extending to the free surface, real or imaginary. Take your fingers on both ends. Go straight up. Stop. That's the volume. What is that volume? That volume plus that volume. That's the volume. Okay, gamma times the volume. What's the top? It's another rectangle. What's the top? Okay, circle, height. Pi r squared. How high is this? R. How high is this? R. Okay, pi r squared, circle. This is cylinder. Pi r squared times r, pi r cubed. This guy here, 1/2 of a hemisphere. 1/2 of him of shell. Okay, you want to convert that guy, this guy right here is, again, d squared, 2r cubed. 2r cubed, 8 divided by 12. Okay, 2/3 r cubed pi r cubed. You can see. Same answer, which means you can play the game any way you want. This is the way the solutions manual does it. This is the way I like to do it. Nobody's wrong, nobody's right, everybody's right. I like this way. How many terms do I have? 2. How many terms here? There's 3. I don't care. Just do it right. What I'm saying though is there's 2 ways to do it. Okay. And one of the key words there was the cylinder is, the sphere is vented. Vented. What does that mean, vented? It means the pressure is atmospheric at the vent point. Okay, now let's go on and take a look at another one. Again, the answer is 8 times larger than the force in 1 volt, so divided by 8. All right, let's see. Maybe I'll take the easier one first. I think I will. I'm gonna work problem 2 from the last midterm. Okay, just to demonstrate again. This was problem 2 from last year's midterm. It was multiple part problem A, B, and C. I won't go through A and C, they're too simple. I'll do part B. Here's the picture. Okay, let's see now. We've got a radius here, R. And this is surface BC. And this is water. And this was given as 1 meter. And R was given as a 1/2 meter. And you're supposed to find the resultant force on surface BC. The width into the page is 2 meters. Okay. I think, I'll work it this way first. Okay. I'm going to take a free body, this is the surface here. Of that little slice of water. That's water. Okay, the weight of the water is right there. Okay. The horizontal force on the left-hand side would look like this. The pressure varies linearly. On top, it looks like this. Where the pressure here is P. There's 2 forces here. There is F resultant vertical and F resultant horizontal. Okay. Now, if you want, let's sum forces in the z direction. That's z. That's how our author does it. Okay. There they are. What kind of forces are there? There's a force due to pressure on top, there's a weight acting down, and there's a resultant force pushing up from surface BC onto the water. So we have F R vertical equal the force due to pressure on top plus the weight. The pressure on the top, here's the free surface. How far down are we? Half, excuse me. This is 1.5. So the pressure where my fingertip is gamma water times a half. Plus gamma water times the volume. There's the volume right there. Okay, that's all. That volume is, okay, here's a square, a half by a half, and into the board is 2. We won't put the 2 in right now, but it's a half times a half. Minus a quarter circle. Multiplied by 2 into the board. That's the volume. Okay. And there's the F pressure. F pressure times area, pardon me. Throw the area in there. That's the pressure right there times the area. I skipped a step. Gamma times H, and H times area. That area is the area over which the pressure acts, my hand. Okay, that area is the radius, 1/2, times 2. Okay. I think I got it right now. Okay. You can put all the numbers in there. Gamma of water, 9810, 5954. Okay. Okay. Now we'll do it another way. Here's the same picture. Now I take force, now I take curved surface BC. Free surface. And I say, oh, by the way, all I'm doing is finding the vertical force because the horizontal one is too simple. The horizontal one is FH, gamma H sub C times A. That's the simple one. Very few people get that one wrong, unless there's a problem getting H sub C. Okay, so that one is a simplistic one. The vertical one's a tough one. Okay. I'll do it the second way. How is this one done again? Take a free body diagram of that little piece of water. Take a free body diagram of the mercury and the shell. Now I take a free body diagram of what? The shell all by itself. A free body diagram of what? The surface BC all by itself. Here's the rule in words. The vertical force on curved surface BC is the weight of the volume of water extending vertically to the free surface, real or imaginary. Okay, there it is. There's the volume, that whole area. Okay. Vertical force is equal to gamma water times the volume. You can check it out and see what's the volume. This guy right here, which is a half times 2. Okay. A half times 2. Oh, do it. It's easier. This is easier. Let's put the volume in here. Let's make it easy for ourselves. Let's take the whole thing. I'm going to take this whole thing, this whole big piece right here. That's 1, okay? 1 there times 2 into the board, okay? So that, this thing here, this is a half, this is a half, this is a half. So, 1 times a half times 2. 1 times a half times 2, yeah. Then what do I subtract out? Subtract out that guy right there. Okay, and gamma water, and that, and the answer for that. Yeah, it's darn close, right? Calculator, round off. Same thing, same thing. Same thing. So, conclusion. Either way works. I don't care which way you work, just work it right. I prefer the bottom way, but that's just me. That's just me. You pick up 3 or 4 textbooks, a couple of them work it this way, 2 or 3 work it that way. So there's no consensus that one way is the best way. It's your choice. Same thing over here. Okay. Any question on that? No? Okay. Now let's go to the hard problem 2.122. Okay, 2.122 again is a submerged surface, but now that surface is a gate. So let's draw that picture. We have a semicircular gate. And then attached to a hinge point here, pivot point. Okay. We have 4 feet, 4 meters and 1 meter. This guy is 1 meter. This guy is 4 meters. free surface to fluids water. When the water depth is greater than 4 meters, the gate opens slightly, unless the water flow under it. Okay, this is atmosphere over here. This is atmosphere up here. Water's to the right of the gate, up to the top. Determine the weight of the gate per meter of length now. He calls length into the board. So if you see width or length, it means into the board. Here's the word width, that means into the board. Here the length means out of the board. So per meter of length. Okay, so I'm going to start that again. And I'm going to do like I did up here. Okay. So now I'm going to take a free body diagram and I'll show you here what it is. Let me move it down some. This is gamma water, and this is the gate. And I'm going to take the free body diagram of that whole thing. Okay. So if I do that, here's the free body diagram. Okay. First of all, I have the weight of the water acting down. Weight of water. Then I have the weight of the gate acting down. I'll just call that G for gate. And then I have F horizontal acting over here. The way we get that, project the surface on there, and in this case, here's the water pressure here. Here's the water pressure. Actually, it's pushing stuff here and here. Okay. And there's pressure on top. This guy here, you know how to get that guy there, it's just gamma H sub C times A, so that's not a problem. And this is pressure, and that pressure force is here, F due to pressure. The pressure, I'm sorry, not up there, that's atmosphere. On top, atmosphere, 0. Left-hand side, atmosphere, 0. Bottom, water under gate. Water has pressure. Okay. And there they are. Okay. Some moments about point O equals 0. Point O is right here. Let's write them down here. I think I call clockwise positive. So the weight of the water and the gate are both negative, minus weight of the gate times D2 minus weight of the water times D1. Then FP causes a clockwise and FH causes a clockwise, plus FPD3 plus FHD4 equals 0. Unknown. Solve for weight of the gate. D1 goes with weight of the water. I'm not going to put all these guys in, but here's D1. Weight of the gate times D2. Oh, I'll put them all in. F sub P times D3. This guy times D4. Do I know all those? Yeah, I can find them. I can find them. I can find all those D's. It's a bit of work, but I can find them. It's a bit of work. When you're done, you get the weight of the gate is equal to 64.4 kilonewtons. Now I'm going to do it again. This time I'm going to do it with a different free body. Okay, this time I'm going to take free bodies of gate plus a little bit of water beneath it. Now I'm going to take free body diagram of the gate. Okay, no, nothing on the top, atmosphere. Okay. So I have, just like over there, the weight of the gate acting at the centroid. I have the horizontal force here. Gamma H sub C times A. And I have the vertical force here. Okay, here's point O. Some moments about point O equals 0. So I have FH plus FV, FV times D1 plus FH times D2 minus the weight of the gate times D3 must be 0. FV, that's this guy over here. That's D1. The weight to here, that's D3. Horizontal times D2, that's here. Okay. The unknown is here. Solve for weight of the gate. 64.4 kilonewtons. Over there, 64.4 kilonewtons. Here we go again. We've done it 3 times now. I've shown you 2 ways to do all these problems. You want to do it, by the way, the solution manual does it. This is the way they do it in the solutions manual. There it is. It's a lot of work. Would you naturally think to make that your control line? I seriously doubt it. I seriously doubt it. You got to see someone work it that way and then say, yeah, I think I understand that. Well, maybe you do and maybe you don't. That way over there, I like, because it works almost all the time. And it's much simpler to see and understand than that way. But I don't care if you see this better, that's fine. You'll get the right answer. If you work it this way, you'll get the same answer. It makes no difference to me as long as you do the work correctly. Oh, there's work over here. Oh, yeah. D2, that's easy. D3, that's easy in the book. D1, that's not easy. D1, that's not easy. Over here, you know, way to that guy, yeah, it requires a couple lines, you know. Not too serious, but a couple lines, you know. So, yeah, and you know, what's D3, half the radius? Not a problem. But to draw the free body of the gate and the water, I guarantee you, most people would never, in a long time, think that, of course that's the way you do it. Yeah, right, right. Okay, just to show you how you get, I'll just show you how you get one of these guys here. I'm going to show you how you get this distance. It's easier, the distance from here to here. I'm going to call that distance x. Once you've got x, you can take 1 minus d1, but you don't need 1, yeah. Take 1 minus x to get d1. Okay, here's how you get x. All right, there is a quarter circle, piece up here. V1, V2. The distance from here to here. The distance from here to here. Centroid, right here. Centroid, right here. I know where they're at. Okay, here to here. Take the area. This is from statics. This is a composite area. Take the area times the moment arm from anywhere you want. I'm going to take it from the left-hand side. Measure the left-hand side. So the top 4 minus 1. This is 3 up to here. Okay. The top piece, well, I'll put it here. 3, 1, radius is 1, so it's 1 up here, left to right. Okay, 3 times 1, this is the area. That's the area. How far from the left-hand side of the centroid? A half. Plus, same thing down here. Take the area, 1/4 pi r squared. R is 1. Times the distance from the left-hand side to where? The centroid, 4r over 3 pi. That's the moment of the areas of each individual piece. Equal the total area times the, we'll call it x bar, to the centroid of the total area. Call it x bar. Total area pi 1 squared divided by 4 plus 3 times 1. Put that total area in there, solve for x bar. Get x bar equal 0.484. So that means that D1 then, 1 minus x bar, I didn't calculate that up, that's what it is. That's the only difficult calculation. It's not difficult, it's pretty straightforward. It's a review of ME 214. So, now, what if he didn't ask you for, what if he gave you the weight, or he didn't ask you for the weight, let's say that he gave it to you. You don't need to take moments about something, maybe. Up here, this method becomes how many forces in the free body? 1, 2, 3, 4. Forces in the free body? 1, 2, 3. Yeah, I like him better. Right there, I like him better. Less forces to worry about. So no matter whether this might be just a solid, let's say the surface is solid. The surface is solid here, you know, and it's not pivoted here. It's just a solid surface. Okay? You got to do it that way or that way. Oh, that's pretty simple. You got FH, FE, take the resultant force as a square root of the sum of the squares. Over here, you first of all have to worry about, you know, this guy and this guy, and once you do that, then you go ahead and take the square root of the sum of the squares. It's okay, it's not that much more work, but it's just not as understandable to the average person as that way is. So I prefer that way, but I don't care if you do it this way on the exam. I don't care. Okay, now, let's take one last thing about these surfaces. And let's see where my little picture is here. I think I've left that one. We'll do it anyway though. It doesn't matter. We'll show it. Okay, here's a surface. I'm going to change it just for simplicity's sake, so it looks better for you. Sometimes people say, well, I don't understand why you put this water above this surface here. What are you doing putting that water up there to the free surface? That doesn't make a lot of sense to me. Well, maybe this will make more sense to you then. On either side, okay, let's assume there's water here. Okay. The pressure here at that point is gamma times H. Now, let's assume fictitiously that there's water over here. Fictitious, there's not water there. Let's assume there was. What would the pressure of that water be right there? Oh, that's a trick question, of course. They're the same, gamma times H. One's fictitious and one's real. So even though I know there's no water over here, could I fictitiously assume there's water going from the surface where? To the free surface? Would I get the same pressure on that surface as I did by looking at the right-hand side? Of course I do. That's enough proof for why you do what I did. Okay, it doesn't matter because this is a fictitious layer of water. The pressure here would be the same as the pressure here, but in a different direction, of course. So it makes no difference. That's where it comes from, real or fictitious free surface. It doesn't matter. It gives you the same pressure at that point. Okay. Now, let's look at one last one. Anything on that before I go on then? Okay. Let's put it right here. Yeah. Okay, let's see. This is, I think, on, yeah, buoyancy. Okay, let me read the problem. 2-137. 2-137. If you are missing any homework, here's all the homework not picked up from people that submitted it. It's graded. It's in my dead homework file. Nobody picked it up. If you want to study for the midterm, be up here in front. This is homework due today. This won't do me any good, of course, as you probably already know. It won't do me any good tonight or tomorrow night. I don't want to see it. You might want to see it for Wednesday. So give it back to you. Turn it back in Wednesday, exam day. That's just to make sure you get it done by Monday so you can study Tuesday for the exam, okay? I'll grade it, but turn it in with the exam on Wednesday. Okay, let's see where we're working on. Buoyancy problems, 3, 120, 135, 136, 137 were all assigned. I'm going to work 2-137. 2-137. Okay, let's draw a picture. There's a picture given in the textbook. So here is a container of some liquid. The height here is H. The area of this cylindrical container is A, and the fluid is gamma 1, has a specific weight, gamma 1. He says that a cylinder is now put into the liquid, partially submerged in the liquid. So the second picture then looks like this. And of course, the water level, this water, I think it's water, rises. Here's the cylinder. Okay, that cylinder, in the textbook, he shows that with a volume V. Yeah. Specific weight, gamma 2. And the water level rises by an amount delta H. And then he says, show that this equation for delta H is true. Show that an equation in the textbook for delta H is true. So, in other words, derive delta H in terms of some of these variables in this problem. That cylinder is floating like that, so it's in a buoyant state. And if we do a free body diagram of the cylinder, of course, we have the weight acting down. And we have the buoyant force acting up. So we have our weight of the cylinder equal F buoyant. And let's see, the weight of the cylinder, oh, I guess, oh, here it is. The weight of the cylinder is the volume times gamma 2. The whole volume of the cylinder, V slash. The buoyant force equal gamma 1 H2 A2 equal gamma 1 V2. And I'm going to find H2. The buoyant force is the weight of the liquid displaced. The weight is equal to gamma times the volume. So, and A2, let's put that up here. A2 is that area. So it's gamma 1. V, what's V2? V2, I'll draw a picture here. There's V2. It's the portion of the cylinder that's under water. No, we don't know what it is. Okay, so now we have to look at those volumes. The volume in the tank final volume initial in the tank plus the volume of the cylinder submerged. Use my hands here. This is the left-hand side. The volume, the final volume in the tank. That's right here, between my hands. That's equal to, now, look at the water around here. That's the amount of water that was over here to start. It didn't leak out. Nobody poured more water in. The water around here is the same as the water, I'll call it water, as the water here. In my hands. Plus the volume of the cylinder submerged, this much, which is V2. Okay, so it's just a statement about the volumes. Okay. The final volume in the tank is the initial volume of water in the tank plus the volume of the submerged cylinder. Okay, now let's go ahead and put those numbers in there. Final volume in the tank is equal to, H plus delta H times A, H times A plus V2. Submerged volume V2, capital H is here. The water in the tank is H times A. The final volume in the tank is between my hands, and the top area is A. Capital H plus delta H A. Capital H A, gone. So from this, I get that V2 delta H times A. I'll look at my delta H times A, there we go. Yeah, H times A, this whole term goes out. Right? Now, take this guy here, take this guy here, put that V2 in for that V2. Here's the equation then, right here, this much right here. Okay? Solve for that delta H. I'll put it in here. Gamma 1 H2 A2 equal gamma 1 times V2 delta H times A. Gamma cancels out. Oh, no, they don't. Pardon me, they don't cancel out. That's the thing there. This gamma over here is gamma 2. This gamma over here is gamma 1. So gamma 1, this was gamma 2. Pardon me. Okay. And so we go ahead and solve for delta H. Okay, let's see where my volume is here.
H2,
Oh,
H2.
H2, yeah, thank you. Yeah, that's what I mean. Okay. Where did, okay, this wasn't in here when I started. This wasn't in here when I started. Yes, oh, yes it was, that was in there. This wasn't in there, and that wasn't in there. So, you have to define other things than he defined for you to solve the problem. And that's the tough part of the problem. How do I know to put in H here? Because you want a volume. How do I know to put in H2 here? Because you want a volume. How do I know to put in A2 here? Because you're going to need that A2 to get a volume. So all those things go into volume. They're not shown in the sketch in the textbook. So that's where people have their difficulty, is that they don't really see where that comes from. Okay, so I think that's all on that one. Let me see if I got the weight right. Gamma 2, which is the cylinder, times the volume, right? Gamma 1 is the water, that fluid, H2A2. H2A2. That came from there. No wonder. Okay. That is a minus sign right there. Minus sign.